This is one of my favorite videos, probably of the entire class so far. It might end up being one of my favorite videos. So I hope you're excited for it too. So remember back in chapter 1, it was not that many sections ago, where we talked about guessing solutions, because if we have a first order linear differential equation, we can solve the homogeneous version, and then we can kind of guess for a solution, a particular solution to the non-homogeneous version. And if we get that, then we can add those solutions and we get a general solution to the non-homogeneous differential equation, which is the original equation. Okay, but guessing was hard sometimes. It was hard to know what to guess. It was hard. We could only really guess for certain functions. And now we are going to take our power of guessing and magnify it with the power of calculus to get the ultimate guess of the power series. So again, you may or may not have seen this depending on whether you've taken Calc 3 or not, but we're essentially looking for a guess that almost always works. And something that Calc 3 tells us is that almost all nice functions have a Taylor series. And what that means is that we can write those functions as an infinite sum, essentially an infinite order polynomial. Okay, so we're going to write that as the sum from n equals 0 all the way to infinity of just a bunch of coefficients times t raised to that exponent. So it's just an infinite degree, degree is the word I was looking for, infinite degree polynomial. All right. So again, there's hopefully there's a lot of alarm bells that might be going through your head right now. So it might be a lot of alarm bells. Specifically, what does nice mean? We're going to ignore that for now, okay? And specifically, whenever you deal with infinite series, we really have to worry about convergence. Many infinite series do not converge. Think of the series 1 plus 1 plus 1 plus 1 plus 1 infinitely many times. That does not converge to a number. It's infinity, okay? There's so many terrible things that can happen with infinite series, and we have loads of theories, or loads of theorems, loads of theory about infinite series and all this stuff. We're going to ignore that too. Okay, we're doing what's called formal analysis, which might strike you as pretty informal, but it's called formal analysis, where we're basically just ignoring convergence and saying, all right, this is probably going to work most of the time. A very applied math thing to do, not a very theoretical math thing to do. Also a very physics thing to do. Not trying to throw too much shade on my physics buddies, but yeah, that's basically what we do. And again, as some reassurance, there are many theorems about why we can do this for differential equations. But again, we're not going to get into that either. Okay, just going to say that, let's not bet anyone's life on this. Let's not build a bridge off of this without checking our theorems. Let's be aware that some of this stuff can fail if we don't meet certain nice conditions, but for most nice conditions, we can do that. All right, that's my big disclaimer here. All right. Now, let's look at a problem. All right. I want you to consider this problem. Consider the problem of dy dt equals ty plus 1. Thank you. All right, so this is a pretty simple differential equation. It's linear. It's not separable. It's not autonomous. It's first order and linear. How bad can it be? Well, you could use integrating factors, and you're going to get run into a little bit of a problem. You're going to get to an integral that you cannot evaluate in terms of elementary functions. So we're going to use, you could also try guessing. You're probably not going to find a guess that works unless you're some kind of math prodigy and you can guess something very odd. I'll show you what the answer to this, by the way. I'll show you what the solution to this differential equation is at the end. But suffice to say, we're not guessing this answer. All right. So if that's the case, And again, we don't even necessarily want to guess, right? This is not a constant coefficient linear equation. This has a t right here. And yeah, integrating factors is going to run us into some problems. Now, what does this equation look like if we write y of t this way? We have infinitely many undetermined coefficients now. What does the differential equation become? Well, the left-hand side is going to be the derivative. And again, taking a derivative into an infinite series, there's only certain times when you can do that. It requires some things about convergence, blah, blah, blah. We're going to ignore that. What would the left-hand side look like if we took the derivative and kind of, didn't worry too much about whether we could? Better to ask for forgiveness, not permission, right? Mathematically speaking, that's not true. In real life, your mileage may vary. We're going to get the sum from n equals 0 to infinity of just all these derivatives. Lots of power rules, right? N times a sub n times t to the n minus 1. And the right-hand side is just t times this plus 1. What is that? I'm going to write the 1 first. The sum from n equals 0 to infinity will distribute the t infinitely many times. And we're going to get a sub n times t to the n plus 1. Again, let's not worry about the question of can we distribute t infinitely many times? The answer is sometimes. And we'll hope that now is one of those times. So what we need to do now is solve this equation. And what you're going to notice, and it's a little hard to see in this form with summation notation, but what you'll notice is that this is no longer a differential equation. This is a polynomial equation. That's kind of the whole point of undetermined coefficients, is turn your differential equation into an algebra problem. This is just an algebra problem because let's look at what we have. Again, let's put this on the next page so we can work with it a little bit easier. So on the left-hand side, let's expand this out. Okay, we're going to get, when n is equal to 0, the whole thing is 0. When n is equal to 1, we get 1 times a sub 1 times t to the 0. When n is 2, we get 2 times a sub 2 times t. When n is 3, we get 3 times a sub 3 times t squared. And then 4 times a sub 4 t cubed. Okay, we got the pattern now. And what does that equal? That equals the right-hand side, which is 1 plus a sub 0 times t. Plus, when n is equal to 1, what do we get? A sub 1 times t squared. And again, we see the pattern emerging over here. A sub 2 times t cubed plus a sub 3 times t to the 4th plus, and so on. Now we need this equation to be true for all values of t. It needs to hold true for every single value of t. So what that means is that the constants have to equal each other. We know that a sub 1, the constants have to equal each other. So a sub 1 is equal to 1. I'm messing up my color coordination, I'm sorry. We know that the linear terms have to equal each other, right? Which means that a sub 2 times a sub 2 is equal to a sub 0. All right, we know that the quadratic terms have to equal each other. And again, you're going to see another pattern, right? A sub 1 is equal to 3 a sub 3. Going on with this, you're going to keep going, and you're going to get, oh wait, hold on, let's write that in the other order, right? 3 a sub 3 needs to equal a1, and then you're going to get 4 a sub 4 equals a2, and so on. Now, something really cool is about to happen. We know a sub 1. A sub 0, we actually do know. My claim is that we actually do know a sub 0. And my claim is that this is actually our initial condition. Right? because when y, all right, y of 0, that means t is 0. And if t is 0, this whole equation, or this whole function over here, when t is equal to 0, this whole function is just equal to a sub 0. All right, so we know a sub 1, we know a sub 0, and every other a value is just in terms of the previous a value. And you could do a little bit of math, right? And you could put everything in terms of a sub 1 and a sub 0. And when you do that, and again, it's a good exercise to pause the video and try to do that, you're going to get a sub 0 is our initial condition. A sub 1 is 1. A sub 2 is a sub 0, which we already wrote, over 2. A sub 3 is a third. A sub 4 is a sub 0 over 2 times 4. A sub 5 is equal to 1 over 3 times 5. A sub 6 is equal to a sub 0 over 2 times 4 times 6. Are you seeing the pattern? We notice we get something different for even and odd indices. All right? And side note, I don't know if you've heard about this. This is what's known as a double factorial. A normal factorial multiplies by all the integers before it, 4 times 3 times 2 times 1. A double factorial only does it for the even or odd. So 7 double factorial would be 7 times 5 times 3 times 1. 8 double factorial would be 8 times 6 times 4 times 2. So it's a shorthand to make this a little easier. And we get something pretty cool when we do all this stuff. So what is our solution? We know all of our coefficients of our Taylor, of our power series, and we know this is what things look like. A sub 0 plus a1t plus a2t squared plus a3t cubed plus a4t4 plus a5t5, all the way to infinity. So when we plug all that in, here's what we get. We get a polynomial that looks like 1 plus 1 over, I'm going to write this as 2 double factorial t squared. And yeah, let's separate this, right? It's one rule for the evens, one rule for the odds. So let's write the evens first, and then we can factor out an a naught. And again, it's going to be plus 1 over 4 double factorial t to the 4th, and so on, plus all the odds. The odds are a little easier. It's just t plus 1 over 3 double factorial t cubed plus 1 over 5 double factorial t5, and so on, right? The odds don't have that a naught coefficient, just the double factorial. And again, combining this, you can see that, yeah, we have a constant term, a linear term, a quadratic term, a cubic term, a quartic term, a quintic term, and so on. And it really just depends on a naught. Okay, so what is a naught for our solution? And again, a naught is our initial condition. What was our initial condition? Oh, I didn't tell you. I didn't tell you, but let's give the initial condition y0 equals 1. All right, that's funny. So infinity is kind of hard. Again, if we're dealing with y, so, you know, y of 0 equals 1, let's, right? So a naught is 1. So we can kind of combine these things. We get that y is essentially the sum, n equals 0 to infinity, of, oh gosh, let's not mess this up. It's 1 over n double factorial t to the n, I believe. Right, and 0 factorial is 1, 0 double factorial, I believe, is also 1. Right. Okay. So this is our answer. And again, Taylor, does this series converge? Whatever. We're not going to pay attention to that. But here's what's interesting. A lot of times we don't actually like working with infinite number of things. So what we do is we look at approximations, right? We could look at the 5th order approximation, right? Which might be n equals 0 to 5, or fifth degree polynomial approximation, right? And that is something that we can work with pretty easily. Like, let's just look at the first 6 terms. Okay. Let's look at this. Let's see this in action. How well do these polynomials approximate the actual solution? So I told you that I would give you the solution. Well, here it is. The actual solution to this differential equation is 1/2 e to the t squared over 2 times the square root of 2 pi times the error function evaluated at t over square root of 2 plus 2. That is the solution to this ordinary differential equation that looks very simple. The error function is essentially a non-elementary function. It's an integral function that we use to, it pops up a lot in, it's like the Gaussian error function is also what it's called. Pops up a lot in probability for integrating e to the negative x squared, which we can't integrate e to the negative x squared by hand. Anyway, this red graph is what our solution looks like. And so our first degree approximation, again, we're centering this at 0. We're looking really at the Maclaurin series, if you've heard of that. Centering this at 0. Here's our first order approximation. Of course, approximating this complex function with a line is not going to be very good. But near 0, it's close, right? And we could look at a quadratic approximation. And again, this is our answer. Okay, I'm writing our answer in maybe some hard to see ways. But disregard here, this is just our answer. Okay, this is what this orange graph is what our answer looks like if we're only looking at a linear approximation. If we look at a quadratic approximation, it looks better, right? It kind of curves for a little bit, curves with it. And again, that would be y sub 2. If we only looked at the first 3 terms of the solution that we found. Let's make it a little obvious, right? What does y2 actually look like? Right, that's n equals 0, it's just 1, plus n equals 1 is t, plus n equals 2 is 1/2 t squared. That's the quadratic I'm actually graphing right now. Y equals cubed, or y3, the third degree approximation, would be exactly the same as the previous one, just with 1/3 t cubed, and so on. So we keep adding terms to get better and better approximations. And this is something very common when we are looking at Taylor approximations to functions is we can keep adding terms to get better approximations, and it's your choice how good you want it to be. But look at the cubic approximation. It's getting pretty good, right? The quartic approximation. All right, yeah, the even degrees are going to be bad, right? Because look at the end behavior. The quintic approximation, 5th degree, 6th degree, 7th degree, 8th degree, 9th degree, 11th degree, 13th degree. Oh, that's 113th degree. That's a lot of terms, but that's a good approximation, right? That's a good approximation. All right, 114 terms. That's the power of Taylor series. Look at that. And of course, if you zoom in, oh my, this is not good on my eyes. If you zoom in enough, they'll be different. This is a lot of terms. Okay, let's not zoom in any further. But that shows, right? Like, yeah, the answer is not a polynomial. The answer to this differential equation is nuts. You're not finding this by hand. We can't even really evaluate this by hand. But we're just approximating it with a polynomial. And if you add enough terms to this polynomial, you get a darn good approximation, and that is cool, to this complicated function. And again, there's lots of cool mathematical theorems about like what functions you can do this with and how accurate they are. And really, essentially, any continuous function can be approximated. If I remember the theorem right, any continuous function can be approximated arbitrarily well with on a finite domain with polynomials. So very exciting. And I'm going to take a moment to take a breath. It's a long video, hard material. What do you need to take away from this video? Okay, lots of cool stuff. So you should take away some wonder. You should take away some excitement and love for mathematics, right? But realistically, right, if you don't love this, what do you need to take away from this video? And I'm going to say is that you should take away this process. Again, we went through it kind of fast of like saying, okay, I can model a function by this infinite series, and I can set this up, right? I really want you to be able to set up the left-hand side and the right-hand side using this Taylor approximation and set up the algebra problem. And you should be able to solve the algebra problem. It's going to be pretty long. Realistically, how much am I going to make you do it? I don't know. But that's the takeaway here is like, okay, we can turn this differential equation into an algebra problem, a pretty messy algebra problem, and you should be able to solve that. And it'll take a long time and stuff like that. That's the main takeaway for this video. But anyway, next video, we talk about another application of Taylor polynomials for solving differential equations. Bye-bye.